sense. And this particular photograph, I didn't actually grow this culture. I have an associate who's doing some work. And this was the first one in white wine. I have probably scores of them in red wine. This is the first one where the filament stage was reached in a white wine environment. Okay, so that gives you an idea of the culture work that's being done in a very brief way. And let me see. Yeah, these don't have the high-level magnification. That other paper does. But back to this photograph. Two main needs, right? The first is to see if you can grow it in a controlled environment. And the second one is, can you stop it? Can you stop the growth? A crucial and fundamental question. Can you stop it or inhibit it? Can you do something? Now, back to the growth stage. This is how this work evolved. But not only can you grow it, but can you affect its growth? AFF, ECT, can you affect its growth? That means, can you maybe make it grow quicker, faster, grow more? And so this is a question going on in the background. And sometimes things happen by accident, again, sometimes by design. It's a combination in my case. But a process was discovered where the growth was accelerated radically. And prior to that time, you had this unknown period of anywhere from weeks, depending on temperature, to likely months, before you would have the stage of growth that would confirm its existence. Well, a process was discovered by which growth was accelerated rapidly, and it involved the use of what are called oxidizers. And specifically, it involved the introduction of iron and hydrogen peroxide. And you can call it an accident, whatever you want to call it, but it happened and I did it. And there was an amazing acceleration in the growth. In fact, it was hard to believe when it first happened as to what was real, because I couldn't imagine something really growing that quickly. But it got to the point where that growth could be produced literally within a couple of hours to where it was detectable under the microscope. And so obviously there were very important questions there about what was happening. How could that be? And what is the chemistry going on that would allow this to occur? And the essence of that chemistry is that particular combination of peroxide, hydrogen peroxide, and iron produces what is called a free radical. Now, I didn't know this when I started. I had to learn. But that particular reaction produces a free radical. Now, the production of that free radical, and it's called an OH, it's called a hydroxyl radical, OH. It's neutral. You know, a lot of radicals have a charge attached to them. This one is neutral. It's an oxygen and a hydrogen and neutral, no charge to it, and it's called a hydroxyl radical. And you can start looking it up as I did. And it produces this radical, and the production of that radical has nothing to do with the culture. You have to understand that radical can be produced with a straightforward chemical reaction of iron and peroxide. So I don't need this culture to produce that radical. But what happened was, if that reaction existed, in other words, if you introduce that reaction into the culture, then the culture took off. It just exploded. And so what that tells us then is that this culture thrives in an environment where this free radical exists. Okay, at least that's the first conclusion. How would you call it? You can call it a hypothesis at that point, okay, if you want. But everything says that it's the existence of the hydroxyl radical, because that is the product of the chemical reaction, that causes this thing to flourish. And so that opens up a whole important subject, okay, because now you're getting into the role of free radicals in our body, and you're having an explosion of growth of this culture with that existence of this radical. So you start asking questions about, does this radical exist in the human body? And the answer is yes, it does. It's a product of byproduct of metabolism. And so what's different here is you had a sort of a chain reaction take place. And see that in the papers that I referenced. It just literally explodes. And so now you have not only controlled growth, but you have accelerated controlled growth, and you've condensed your study time period from what was weeks to months to literally a case of hours to a couple of days. And so this is a huge advantage in terms of the progression of the work. And then what happens after you understand the nature of the reaction that has allowed this to occur, then you start thinking in reverse. And that is, if I can do something to accelerate this growth, and I understand, and that's the crucial part of it, I understand the basis of what caused that enhanced growth, could I do something now? Is there an idea that we could have to cause the reverse and inhibit that growth? And this is my thinking process, right, as I go through. And it's a combination of circumstance and reason and logic and research, luck and intuition, all of these things. There's no easy path to it. But that's the idea. If you understand it, what will reverse that? And so the thing that comes to mind, of course, is, all right, what is this hydroxyl radical? And how do you get rid of it? Is it possible to get rid of it? And so I began doing research on that, and I'll give you the buzz phrase so you can cut through some of the time that it took me to get through it. But a buzz phrase here would be a hydroxyl scavenger, okay, or a free radical scavenger. You're looking for something that will tie up that radical, which will basically, because they're very reactive, they want to react with things. So you want to provide something for it to react with to neutralize it. And that's a term that will get you on the right track of learning about this process. And I did work, and some of the papers were pure medical journals where you only get the abstract, and you unfortunately don't have the whole paper, and you have to infer as much as you can from a paragraph at most, to digging into the biochemistry books and understanding the nature of what's going on here. But I started running a search. I started exhausting the literature for whether or not is there anything that specifically and directly targets the hydroxyl radical. And I dug and I dug and I dug. And I came up with a list of candidates, I would call them. On that previous paper called The Discovery and a Proposal, in the reference list at the bottom, you will see the majority of those papers or sources that I encountered. And we must understand that this list that I have worked with is not intended to be exhaustive at all. It is intended to test the idea. That is its purpose. If you truly understand the reaction, and if the idea is correct, the hypothesis is that a scavenging or neutralization of that radical might inhibit its growth. So I have three, and I'll try to close this off pretty soon, but I have three particular hydroxyl scavengers, as indicated in the literature search, that I have investigated. And I anticipate that there would be many others. This is just the list that I have started with. And the list specifically now at this point includes ascorbic acid, basically vitamin C, glycerol or glycerin, which is interesting. And when I say these, you will see, if you read my work, you'll see where it came from. I didn't invent it. It came from a direct paper of some type that stated that this particular substance was beneficial in neutralizing or scavenging the hydroxyl radical. On my side, of course, I am attempting to find things that will be compatible with biology, but everyone will have to decide that for themselves over time. But ascorbic acid, glycerin or glycerol, and the third one was a pick of one item out of a list of potentially thousands. That's another whole topic. But the particular one that I picked was, it wasn't actually identified in the paper. It was the reasoning of the paper that I used to employ what is called sodium citrate.